Developers are moving away from writing syntax by hand. The industry is moving towards agentic engineering, where your job is to orchestrate AI agents that write the code for you. The promise is massive upfront velocity, the ability to build functional SaaS applications from scratch in a matter of days. But that speed often comes with a price. Teams are uncovering unexplained bugs, duplicated logic, and security leaks buried inside their repositories. While these tools boost initial output, they also front-load a significant amount of long-term technical debt. This chart compares defect survival rates. GetClear and Jamea systems data shows traditional reviews catch most issues, but AI-introduced defects have a 22.7% survival rate. Over 3 years, refactoring dropped from 25% to 9.5%, while cloned, copy-pasted code has sharply risen. Once those surviving defects hit a production environment, the cost to remediate them multiplies by 15. AI systems inject compounding maintenance debt at a speed that human review cycles cannot match. Vibe coding often starts with a brainstorm-first approach, using natural language to outline your goal to the AI. Within seconds, tools like Claude generate instant, shareable HTML and React UI components without you writing a single line of code. However, these standalone artifacts are isolated. They cannot natively connect to live databases or pull from external APIs. To scale this into a production environment, you usually have to discard the generated code or port it into an enterprise platform like MindStudio to avoid lock-in. Prototyping speed is a misleading metric if the resulting code foundation is entirely disposable. Advanced IDEs like Cursor 2.6 change the workflow. Here, you deploy long-running agents, or composers, to implement complex features across multiple files. The result is rapid codebase expansion and immediate feature deployment. But these agents eventually suffer from context rot. Over a few hours, the agent's internal map loses sync with the actual state of your disk files. This creates the revert bug, a race condition where an agent review can silently wipe out a developer's manual code changes. This line graph shows standard subscriptions giving way to dynamic billing, triggering exponential cost spikes when agents loop. Frontier models drain budgets rapidly, while alternatives like DeepSeek V4 Lite maintain a lower, flatter trajectory. Using these tools often trades the effort of typing syntax for the burden of auditing massive pull requests and managing high financial risk. In 1992, technical debt meant a deliberate shortcut to meet a deadline. Today, AI generates accidental, unprompted debt without an engineer making a conscious trade-off. This illustrates cyclomatic complexity drift. Instead of clean helper functions, LLMs nest complex logic in line, creating a tangled web. These fractures represent maintainability issues, like bare accepts swallowing errors, and unencoded file opens crashing inconsistently. The risk extends to security. AI generations frequently omit critical safeguards, like Postgres row-level policies, which directly leaks personally identifiable information. AI debt builds through structural accretion, slowly rendering the entire codebase unmaintainable. Deploying these tools safely requires matching the specific AI workflow directly to your actual technical capability. For non-developers, the rule is strict isolation. Keep tools like Claude artifacts restricted to standalone calculators, dashboards, or single-use prototypes. You must treat this generated code as disposable. It cannot serve as a trustworthy backend foundation. For engineers, use strict .cursor rules files. These force the AI to respect your project's existing architectural constraints. You also need a defensive commits protocol. Manually commit your work to Git before every single agent run to protect against the revert bug. To protect your budget, default to DeepSeek V4 Lite for 80% of routine tasks to avoid max mode cost spikes. Applying these specific constraints neutralizes the risks, keeping workflows fast without compromising the system. Engineering leaders must now actively track and metricize AI decay before it merges into a production environment. This dashboard highlights the metrics you need to monitor. Alongside traditional velocity, track clone density and the survival rate of AI-introduced defects. You also need OWASP-mapped scanning targeted at AI-generated code. As this gauge flags a simulated pull request, it blocks a security leak from passing deployment. Leaders must be willing to throttle perceived AI velocity to enforce these rigid checks. Orchestrating autonomous agents means trading the short-term hype of instant code for the long-term survival of your architecture.